So, welcome everyone. I decided to not wait anymore. I will talk a lot anyway, and people who join later will find interesting information anyway. So, I think we are ready to go. So, welcome everyone. I'm Endre Varga. I work at Typesafe at the Akka team, and I will talk about distributed systems in this session. This is a very special talk to me. It's kind of very personal. So it's my personal message, if you like. Or I would even say it's a kind of a documentation of my journey at this point into distributed systems, and I share it with you. And hopefully I will guide you to the first step of your journey as well. So for me, this whole thing started a little bit more than 1 year ago. I was still a new employee at the Akka team, and it was we had a meeting where we discussed certain aspects of clustering, which was at that time still experimental, and we figured out some things still. And after some point, it was evident that while we understand many pieces of what we are doing, and it was obviously working, but there is a difference between understanding and deep understanding when suddenly effect and all lots of its consequences become evident, and you start to really get the gist of it, or as hackers say, you grok it. So that was my first day when I had this spark of enlightenment, because I ended that day with a draft of a proof of a certain property of that system. While the proof itself is not important, it was my first step of getting a real grasp of how things work. Now, the second step was when my colleague, Björn Antonsson, also from the Akka team, submitted a pull request where he basically optimized our gossip protocol message size by removing certain vector clock entries and replacing them with a simple Boolean flag. Now, he figured out why that works, but when we reviewed his code, were completely confused. How can this even work? I mean, lots of information was just removed from those entries. And again, that day ended up for me with another proof draft, which basically explained to me not just, I mean, you try it out and you see the pieces work, but suddenly I got the message why it works. What is the thing behind it that makes it work? And the third and final step for me was reading a book about epistemic logic, which you won't find it here directly, but the whole presentation is about the epistemic viewpoint. And so we will start the journey now with me. So this talk is about how to think about distributed systems, or we can even reverse it, how to not think about distributed systems, because sometimes this is the most important part. So first of all, I would like to ask a question for you. Please raise your hands, everyone who worked with or developed or used distributed systems. Is there anyone who hasn't raised his hand? Because you have also used distributed systems. I'm very, very sure that you have used. So what is actually a distributed system? I have a simple definition here. It's not a formal definition, not the only definition, and not the final definition, but it's enough for this talk. There are several important properties which make something qualitatively different, which we call distributed, and these are the main points. So first of all, a distributed system consists of components that are concurrent, which means that they can progress separately from each other independently without necessarily having any synchronization points. Another important thing is that they communicate over a lossy channel where messages sometimes just disappear and don't arrive where they intended to arrive. This is one of the other key aspects. Non-deterministic communication delay. Now, why is this important? Because if you have deterministic delay, then you can build a global synchronized clock. And from that point, you have no more problems. But unfortunately, this is not possible, or the issue can be sidestepped, but this is out of the scope of this presentation. And there is another final thing, is that the independent failure of components. If something fails and everything goes down at the same time, it's no longer a distributed system, at least in the scope of this presentation, because then individual failures do not matter anymore, because there's no such thing as individual failures, and all of the talk is about how to deal with individual failures. So what we usually want when we go to distributed systems is to have something that behaves like a local system. It's just larger. We know we add some nodes, so it becomes faster, it becomes more resilient, maybe more maintainable, but it's just somehow the same thing just in a different scale, right? And can we actually get what we want? And this is the discussion tackled in this presentation. So there is one very basic problem. You might learn about it at university or other schools, because this is one of the most basic problems in distributed systems, which sometimes called two armies or two generals problem. And it's about two entities trying to coordinate an action. In the original formulation, you have two armies, which are separated by a hill, a valley, or fortress. It doesn't really matter. And they're individually too small, because between them there is a larger army or a fortress which they individually cannot attack. They will perish. So they need to have a coordinated attack at some point. So they want to agree, and all they can send are messengers that try to go through enemy lines, and sometimes they arrive, sometimes they don't. So we try to solve this naively. And we have two entities. They want to coordinate an action. One of them said, I want to do this action, and then he performs the action, and eventually the other entity gets the message, and he also performs the action. So far, it's fine. Unfortunately, in reality, there are actually two scenarios that are possible. The first scenario was the naive one, which I showed earlier. Message goes through, both sides execute the action. Unfortunately, there is another scenario when the message doesn't get through. So entity 1 sends a message, it doesn't arrive, so entity 2 doesn't even know about the intent, so he will do nothing. Although we define the protocol that entity 1 will start executing with the action immediately after he sent the message. So now we have an inconsistency, only one army will attack, and unfortunately that's an undesirable state. So we try to fix the protocol. And now we want to have an acknowledgement for our message, because that was the problem. We sent the message, and we didn't know whether it got there or not. It was indistinguishable from the viewpoint of entity 1. So we fixed the protocol by adding an acknowledgement. Now it should look like something like this. Entity 1 declares its intent that I want to do some action and sends the message. Eventually, hopefully, it gets there, and entity 2 agrees and sends back an acknowledgement, yes, I agree, we should do action A. And then when entity performs action A, and also then after receiving an acknowledgement, the first entity will execute the action as well. Again, unfortunately, there are another hidden scenario which is incompatible with the previous naive scenario, when the acknowledgement is lost. Now again, the problem is that we said that entity 2 will execute the action immediately after he sent the acknowledgement, but unfortunately entity 1 didn't receive any kind of acknowledgement. And what is important from the viewpoint of entity 2 who sent the acknowledgement, the two scenarios are indistinguishable. If you would put your hands to just hide the other half of the slide, the arrows look exactly the same. You cannot distinguish between the two states. So the problem is that even though we added an acknowledgement, it didn't solve our problem. And if we think it through, adding an acknowledgement to the acknowledgement will not solve the problem either. Because there is always a final message in the protocol flow. Let's call it the final important message. Why would I call it like that? Let's say it's not important. then we don't send it, we just remove it from the protocol. So at the end, there will be one message that is important, because if it gets lost, then we don't do the coordinated action. So that's why it's important. And there is a final one. And as we have seen, we cannot know that it has ever arrived, so we need an acknowledgement, which now becomes the final important message. So no matter what we do, we cannot tackle this problem. It's simply impossible to safely agree in this case. So now we ask the question again. So when we want to look at distributed systems, like just larger and scalable local ones, is it realistic? Well, obviously not. But we can make some important observations. First of all, I think everyone has in this room this nagging feeling that adding more and more acknowledgements somehow must be containing more information. There is some piece missing here. We will find that piece later, but this is an important observation. Don't freak out. You are on the right track. The other problem was that we declared that we want two entities to execute the same action in a coordinated fashion. Now let's make a thought experiment and simplify our problem. When we don't require the two parties to execute the same action, we only require one of them to execute the action, but we require him to only execute after they have reached agreement. This is different, because we can change to a simple protocol where entity 1 sends the intent, waits for the acknowledgement, and when he gets the acknowledgement, he executes the action. At first, he fails because even his intent doesn't get through. On the second attempt, it still fails because the intent went through, but the acknowledgement has been lost. But since the entity 2 haven't executed anything, so far so good. And finally, under the assumption, of course, that eventually we can get messages through, we get back the acknowledgement and we execute the action. Now there is something very, very interesting and hidden in this message sequence chart, notably that at this point, both sides were in agreement already. Because entity 1 obviously agrees with himself, and entity 2 already received the intent and went through that if statement and declared I agree to it, just the message was lost. So we reached a desired state, but we have absolutely no idea that we reached the desired state. And this is the most important slide in my whole presentation. I read it out. If a tree falls in a forest and no one is around to hear it, does it make a sound? And the core idea is there is a whole world of difference between a state and an actually observed state. These things are completely different. So we can reformulate the question. If a tree falls in a forest and there's no one around to hear it, does it actually matter? Do we care? So let's expand the toolset we have to analyze these kind of problems. I introduced some pseudo-formal notation which describes different states of knowledge. So we can talk about the fact X, which is some kind of statement that can be true or false, for example. We can say that this fact is distributedly known if we can pull some other facts from the system, assemble together, and now get the fact. One nice example, one database knows my user ID, and the other database has a mapping from user ID to an email address. So now that the fact that my name is Endre Varga, and my email address is endrevarga@typesafe.com is distributedly known. Because in one database, it knows that this user ID means Endre Varga, and another database knows that this user ID has this email address. But it's never put together yet, so it's just distributedly known. We can also define someone knows, which is, I think everyone could imagine that. And there is the biggest thing when everyone knows something. Now, to understand these concepts, Let's go through with a very simple example where we will aggregate some fact in a central node in a small toy cluster, and then we will try to disseminate the integrated knowledge. And we will track how the states of knowledge will change. So I will call the dedicated master node to be primary and all the others secondaries. So at this point, we have two secondary nodes, S1 and S3. They all know these subfacts A and B. Can be my user ID and name, user ID, email address. But at this point, no one assembled this together to the compound fact X. So these two nodes send these information to the primary, and the primary will assemble it. And now at this point, someone knows X. Before it was just distributedly known because the pieces were not integrated. Now the messages arrive to the primary. Now someone knows X. At this point, the primary decides to let's distribute this assembled information X to the other nodes. It can be a cache, for example. At this point, if the messages arrive safely, everyone knows X. But no one knows that everyone knows X. Now, you might think this is mind-boggling, but it isn't. I give you a very simple real-world example. A couple of friends going to a pub, and they all know a gossip, namely that one of their colleagues is going to get married. They all know this fact, but they all know this is kind of secret, they want to have a surprise, so they don't want to spoil a surprise. But since no one in the pub knows that everyone knows this secret, they won't chat about it. Although they can all safely chat since for them it's no longer a secret and they wouldn't spoil anything secret. So it's very simple, and politics, for example, use these kind of states of knowledge all the time. So now if the secondaries actually acknowledge that they received the fact X, and these acknowledgements all safely make it to the primary, now the primary knows that everyone knows. So from the global viewpoint, we can say someone knows that everyone knows that X. You see, there is this nice progression, distributedly known, someone knows, everyone knows, someone knows that everyone knows, and so on. So this is where your X go. You remember? They add the information, just not what you expected. So what we have seen is kind of a simple form of consensus, if you like, not like Paxos or Raft. This is not just a thought experiment, but still, it was kind of a consensus protocol which started to build up layers of knowledge, and it sidestepped some issues from the two armies problems. Namely, we used one concentrated point where we collected the knowledge we wanted, namely the primary. Of course, in real world it can fail, so real world it's even more scary. But so far, at least we learned something. So let's go back to our dear armies, and let's analyze, because that's the core of every distributed problem. So if you look at the progression of messages, it starts with entity 1 knowing some fact X, then sending a message which makes entity 2 knowing X and knowing that everyone knows X. And of course, sending the X of X and X of X of X of X. I need to change it to epsilon or something. So anyway, so eventually it builds up layers of knowledge which becomes very, very evident if you suddenly relabel the knowledge. Instead of having these whole nested expressions, at every point we just add the new letter to denote what we want. And now we can absolutely see how one round trip adds just one another layer to the other. And this leads to this image, which is the cone of the past, which represents a very important relativistic viewpoint in distributed systems. The more detailed and layered knowledge you want about the system, the farther in the past it actually comes from. Because every layer of knowledge has a cost of several round trips. several messages sent, so it adds delay. So more layers you want, later you get it compared to the original inception of the fact. And what we actually see here is introspection of the system to itself. If we look at the cluster, not as a set of individual entities, but some entity on itself, it's kind of a self-awareness, not like what we have, but still, it's hard to deny. It's grabbing pieces of information about itself. When we say everyone knows that everyone knows, we are arguing about its own state. The cluster proves things about its own state. And that's how I view things. So far, so good. But we need to have one more sidetrack. And for this, I chose an example of the quorum. So far, we have seen layers of knowledge. We have seen how it becomes more and more delayed when we want more layers of knowledge. But we have to learn something about time again. So quorum, again, simple primary, secondary scenario. It wants just to send messages to all of its members and declare that it has been successful if the majority of these secondaries acknowledge the message. So at the first step, it tries to send these 4 messages. 2 is already lost. S2 and S3 will never receive them. S1 received it, so from the quorum, we have already 2 nodes, the primary itself and S1, but there are still 3 nodes that don't participate, so it's not yet a full quorum. So S1 is very quick, acknowledges a message, but we still don't get the message for S4. So primary now sees the acknowledgement from S1. And at that point, S1 fails. And immediately after that, S4 gets the message. And of course, he will acknowledge it. And now, what does the primary see? I sent out 4 messages. I got 2 acknowledgements. We are 5. I am 1. 2 acknowledgements. We make it 3. That's a quorum. There has been no quorum at all in the system ever. What's wrong here? Well, what's wrong here is how we think about the thing. There is a difference between state and observed state. I cannot repeat it well, I can repeat it anyway. And this is very evident here, because on one hand, we have looked at the message sequence and we said there is no quorum. But all the participants in the system observed a quorum. And now we reach the point where we find a fault in our mind, namely, which I usually call the assumption of an omnipotent observer. The omnipotent observer who looks at the message sequence charts and declares that I see everything, I know what the real truth is, but this thing doesn't exist. Not your system, not your ops people, not your monitoring tools, not your hosting provider. No one ever is an omnipotent observer. If you cannot observe something in a distributed system, it simply is not there. So how can we now define present? So if we look at this very simple message sequence chart, which everyone who ever used distributed systems, I think, is familiar with this kind of scenario. So entity asks about the state of entity 2, which he replies, but immediately after its state changes. So at that point, state A is observed, the actual state is different. But does it really matter? It only matters because we look now like this omnipotent observer and we declare a global time. But they don't observe the global time. For them, it's reality. So present is volatile and subjective. And if we revisit our cone of the past, then now we can add some annotations on it, that at the tip of the cone is the local present. The local present is observable, and it's immediately available, well, by definition, if you like. But everything else that we call present about the global state of the system is actually a past point in that cone. The observable, possible past points, the set of those. So in a distributed system, there is no past or present. Everything is subjective. And then you might ask the question, can the past change? Who would say yes? Please raise your hands. Okay, not that much. Yeah, so I would give a quote which I didn't put on the slides because unfortunately it's kind of historical, political, but it's important anyway. Who controls the past controls the future. If your system goes down and you alter the database and the system comes back again, can it distinguish that you altered its past by changing the persisted state? Up. Yeah, I forgot my quote. But there is some very real-world example I realized because I have a 7-month-old boy. And you know, people make this sort of thing, writing a journal about the baby. Like, this is the day when he first smiled. This is the day when he first started to grab things. But eventually you realize that you don't have time to make this journal. You don't have time at all. And at some point, we forgot to put this into the journal. When was it exactly? Well, and then you put an entry in your journal like estimating the date. And then you realize that like 10 years from now, I will not remember it. I will just look at the journal and this is the date and I'm happy about it. And this is how it works. And this is actually a nice tool that we can use. Which leads to our question, since now we have no past, or at least no objective past and no objective present, and we have only layers of knowledge which also have to suffer some delay, then how can we define consistency? Because that's usually what we want to achieve in a distributed system. And the solution is, again, to invert the question, how can we define inconsistency? So in a distributed system, inconsistency means that I did something and then I observed some effect of some fact, and then later I observe another fact that contradicts the previous one. So for example, I sent a write to a database, I got back an acknowledgement, and then I send a read to the database, and I come and I get back a different value, although, for example, I know no one else has been writing to that database. And that would be a refutation of my conjecture that I actually have written to the database. That's what you would call inconsistency. Inconsistency just means that certain pieces of knowledge can be refuted in the system. So in other words, a consistent system is which who cannot observe refutations of its facts. So in this slideshow where there was this quorum example, where we have seen that one node can observe a quorum, although from the omnipotent observer's viewpoint, there was none. Now the problem is that in the real world there is no omnipotent observer, but it might be that several different nodes, we have only one primary in that example, but it can be that multiple ones observe, one observes a quorum and the other does not. But if we define our protocol that way, that is impossible, then we simply sidestep the issue. Because we declare the quorum, it's a declaration, and no one else can refute it, then it's consistent. And again, we need to throw away this kind of built-in notion of global reality, a global truth, because it does not exist. We cannot observe it. Well, okay, in the real world you can have a philosophical discussion whether things exist or not, but from a purely technical viewpoint, it doesn't matter. So one very important advice: when you design a distributed system, you never strive for a consistency definition or requirement that defines consistency from the viewpoint of an omnipotent observer, because there is no such thing. So, to finish my presentation, I assembled a simple example, which is again not a real-world production-ready protocol, but it shows certain ways how you can exploit this layering of knowledges, and also we had this idea of centralizing the action. Now I show that it can be done in a more decentralized fashion if certain assumptions are met. So you want to have a simple form of consensus, again, not Paxos, not Raft. It's just a very simpler thought experiment. We want to have to execute an action, but only after some premise of it has been confirmed by everyone, so everyone agrees that the action can be taken. Now we don't have primaries and secondaries, all nodes are equal. At some point, one node decides that he wants to execute the action A, but first, of course, we need to be sure that everyone agrees on the premise B. So he tries to disseminate this information, and for this example, I chose gossip. Gossip means that I just randomly pick some other destinations, and I send messages to them. And then, they, in turn, will start to send messages to other nodes as well. It's randomized, but eventually, everyone gets the message. So this is gossip, and we are still in the someone knows state. Eventually, the gossip finishes in that sense that now everyone has been infected by the message. So we reach the state where everyone knows the premise and knows that they agree on. Everyone knows that the action has been proposed and the premise is true, but currently no one knows that everyone knows. So we cannot execute any kind of action. So we now enter a second phase, when not just we gossip the content of the message, the premise and the action, but we also add from whom we have heard this gossip before. So to give an example, I get a message from Julia and Kim, and then I will send the message to Joe, but I also include the information that I have seen this message, Julia has seen this message, and Kim has seen this message. Now, all that crazy arrows is this second phase, which if I highlight it becomes more evident, that eventually there will be one or more nodes that will observe a gossip which have the full table of participants, meaning you have a table where everyone has declared that he has seen this message. Now at that point, basically N1 and N2 knows that everyone knows P. Because at the first stage of the gossip, we reach the state where everyone knows, and through the scene table, which are kind of the individual acknowledgements, we reach the state where someone knows that everyone knows. But the key difference from our primary secondaries example, that we haven't decided up front which node will concentrate these kind of information. They just emerge randomly due to the randomness of the gossip protocol. Now, at this point, we have two nodes in the desired state, and they just need to execute the action. There is one more important trick here. The action must be a pure function of the premise. It cannot contain any local information of the node that was not contained in the gossip message. because this guarantees that even though we have multiple nodes executing the action, it will be the same action. No parameters can differ. And that's how it works. And this ends basically my explanation. So I end with some advice. So there is this generic advice, which you must repeat every time because it's so important, that you need to have a failure model. What do you assume to be fail and what do you not? It's fine to explicitly say, I assume that messages don't get lost. You made the decision, you take the risk. But that was a decision. It's completely different when you ignore the fact that your message can be lost. That's not a decision. That's just playing with fate and hoping for the best. Never assume reliable communication. This is obvious from the previous slide, I think. But there is one important counter side to it. Sending a message does not introduce information to the system. Receiving a message does. Sending does not. It's very important. Of course, you should never assume infinite layers of knowledge. In the two armies examples, we tried to do that. We had always one last important message, which now we can translate to adding to a new layer of knowledge. So it's tried for basically getting an infinite layer of stacked knowledge layers at the end. It even has a name, this kind of thing. It's called common knowledge. So common knowledge is when everyone knows that everyone knows that everyone knows ad infinitum some fact. This is impossible to achieve in distributed systems. Global state is different from observed global state. So again, forget your notion that you look at the message chart and some state was achieved. It doesn't matter until someone actually observes in that real system. The message sequence chart always represents an omnipotent observer. It's a very good tool. Don't drop it. Omnipotent observer is a tool for thought experiment. But at the end, your running system will not contain such an entity. And that concludes my presentation. And now you know why it was titled Without Past and Present. Because local discovery of the global past via cooperative distributed proof while writing the global present is actually how distributed systems work. Thank you very much. And now some final words, because someone from my previous presentation, after viewing it, asked for some happy ending. So, as I started this is a journey. It is also my journey, and now yours. And you are at certain points of your journey. Some people just, now I go back and do my stuff. The second step will be you are scared now. How could even systems work? And then there is this nagging feeling that systems actually do work. We use them day by day. And then at the last step, you realize there's nothing wrong with the systems, nothing wrong with the world. We just sometimes try to force this global, absolutely existing Platonical view of the world, the distributed systems, which is just wrong. We can actually guarantee stuff. We just need to look at the right angle, and then we are fine. So welcome to your new journey. Hope you enjoy it. And now we can have questions, I think.
Why do you not consider timeouting in your protocol, basically? Because so you're assuming what message could be delivered very, very long time.
Yes.
In reality, it's usually message either not delivered or delivered within some time.
Yeah, this is about assumptions, right? So unbounded message delay, which is not infinite, just it can be arbitrarily long, is indistinguishable from message loss. But you're right that if you can assume that a message and an acknowledgement must have been arrived under a certain time because you know your system enough, you built in these assumptions, which is fine. If it's violated, then it's wrong, but if you know enough, it's fine. Then of course you can have timeouts. And timeouts relate to another concept which I didn't cram in here, is about beliefs. So this presentation was only about knowledge, with things which we cannot refute anymore. We learned it's true, it remains true. Sending a message doesn't introduce knowledge, but might introduce belief. I might believe that it's very plausible that the message got through, but beliefs can be refuted. And that's fine, but you need to track it. To give some example, if some system declares the other dead, it might come back. And that can be problematic. So usually it's a declaration. So I believe the other system is dead, and I won't accept any refutation. You are dead. Go away. Don't come back. It's actually very relevant in practice. So yeah, beliefs are a new step in the journey, I would say. But yes, timeouts are very important. So I hope this answers your question. Anyone else? Okay.
So you just mentioned that it's one way of handling these situations is to say that if I believe another node is dead, then I won't accept connections from even if it comes back.
Mm-hmm.
And this is great because then you have monotonic set of knowledge that
Exactly.
grows, but that's not actually how networks work. So how do you model that? That nodes can go away, they can come back. There's no guarantee that.
You say that they are new nodes. And then we'll make your knowledge monotonic because you said that node was dead, but this is a new one.
But
Practically, it looks the same, but it's not exactly the same.
okay, but then that means that different participants in the system actually think that the list of participants is very different, right? So you go away and come back, and I'd say you're a new Endre, but there's actually another person who sees that it was you all along.
Yeah, you have to disseminate the declaration first that that guy is dead, don't talk to him, and then reintroduce the old new node to the rest of the system. But so the thing is, you might be fine with another system going up and down. It depends. It depends if you did an irrecoverable action, like you notified everyone that he's dead and they are out of your control, different team, different systems, then you cannot recover. If you can recover, then it doesn't matter that your knowledge is non-monotonic, because it's fine. So with the two armies problems, that was another issue, that once one army attacked and the other did not, then it perished and you can never recover. ATM can be similar, because when it disposed the money, it's done. You cannot get it back. But in other cases, you can actually revert things. So yes, this is another layer, I would say.
Would be any broadcast message basically review the picture, or it's basically similar to unicast? Because in your system, messages are more or less unicast. So you send to node
Mm-hmm.
message. But how would it change if we introduce broadcasting?
Broadcasting will not change it that much, because in reality, even if you broadcast, it's not globally synchronized, so there will be delay when it actually receives to the entities. So broadcast doesn't change the picture that much. Especially if it's lossy and then delayed, it's basically the same.
Yeah, but if I number all my states and I basically broadcast my state is this one, and everybody who sends this message also broadcasts what I see him, and his state is this one. So it's kind of broadcast to everyone's state.
Well, the question is, who is everyone? Well, if nodes come and go, then all individual nodes have different views of who is there and who is not. So the problem is that even everyone, which I sidestepped in these slides, is not a well-defined term. I addressed it in the quorum example a little bit, that it's defined subjectively, that to my local knowledge of that these sets are nodes which I'm broadcasting to, I can assume that this is, if I got a reply from everyone, for example, that everyone knows. but the membership might have changed between those time points from the omnipotent observer view. Any more questions? Yes?
Although in the general case, it absolutely makes sense to not assume a distributed clock. However, is it reasonable to, for example, in Akka, given the speed of typical networks these days, to be able to assume that a global clock can be approximated? And if so, what algorithms can take advantage of this fact?
Well, this is not a simple question. So if all of those who wrote the Google paper, how they handle it, they don't handle it via the network. They have atomic clocks and they use the GPS system to synchronize between them. So I don't think the network gives you enough resolution. You can synchronize up to some point. I can say, my assumption of the network delay is this distribution, and then you can go down and down, but you cannot go below a certain drift. And if you have concurrency, granularity that is smaller than that drift, then it will not work. Another problem is sometimes network delays, like in virtualized environments, can be long-tailed, which means that an average might exist or not, or it might take forever to converge on an average. Average delay, I mean. Okay, it seems like everyone has been scared enough. No more questions, but you can hunt me down in the halls, wandering around, and then just we can continue. So thank you very much.